given this circuit. And if I don't give units, it's going to be the basic units. It's going to be ohms or farads. So the question is, find V of t and I of t for all time. So where to begin? First, categorize what type of problem it is. Now, the order of the problems that I give will be the same as the order of the problems that I told you on the objective sheet. Which type of problem is this?
Our first order circuit.
First order, because stuff is changing right here. Oops. Looks like I forgot to write my current source. Okay, so let's start it. What is always going to be step number one with these things?
To find the voltage across the capacitor before time equals 0.
Yeah, exactly. So the first step is going to be to draw it for time less than 0 and to find VC naught. That's it. No matter what you're asked to find, you're going to do that. By the way, let's see, I don't think I drew where my I is. I need to do that. So there's my I of t. Okay, so we're going to draw it for time less than 0. The capacitor becomes a, what do you say? An open, definitely an open. And because it's an open, do I even need to draw it? It's got no current going through it. It doesn't affect the circuit. So do I need to draw it? Dontre, what do you think?
No, sir.
Oh, think about it carefully.
You said since it's open, do you need to draw it?
That's right. If you don't draw that, then there's no way that you can write the voltage across it. And if you don't write the voltage across it, then you can't find VC naught. And maybe you'll end up finding the voltage across this or someplace else, but you're not going to know where to find that voltage. So even though there's no current going through it, and even though it does not influence the rest of the circuit, you still got to draw it because this is what you're trying to find at the end. And it's the only thing you're trying to find when you're drawing it for time less than 0. What position is the switch, up or down?
At t equals 0 is down.
At t less than 0. This is that
0.
region that we're drawing it. Time less than 0 here.
Oh, at time less than 0, then it should be up.
That's right. You know, we always start by drawing it for time less than 0. So it's up. We shouldn't have any switches, no U of T's for time less than 0. We get this circuit. Okay. I can see where my current is flowing, right? You can just sort of imagine that some of it's flowing in that loop and some of it's flowing in this loop and none of it's flowing through this loop. So we need to find VC naught. What method will you use, Bobby? Remember, our goal is to find VC naught. We drew it for time less than 0. We need to find VC naught. We got this circuit. It's kind of complicated. I can't just look at it and say VC naught equals 6 amps, say. So what method will you use to solve for it?
Would you find it through the 6 ohm resistor, and then would that be the same as VC naught?
You're absolutely correct that if you know what the voltage is across that 6 ohm, that'll be the same as VC naught. What is that voltage by inspection? Right, you can't see it by inspection. So what is your method to find VC naught, which is the same as the voltage across that 6 ohm resistor? What will you do?
Source simplification first.
Source simplification.
You can just like add
So you can source simplify.
Transformation.
Yeah, that's it. That's it. Hey, is this one of these trivial circuits, these degenerate circuits, or do I need to do a true source transform?
you can turn that into
You can do a true
True
source transform.
You got to do a true source transform, right? So we'll source transform everything to the right of those 2 wires. Good thing it's only 2 wires. I couldn't do it if it was 3 wires. Wait a second, aren't these resistors in series? Aren't there some resistors in series here?
Yes, because there isn't any current flowing through the VC naught.
Right. So you could say because there's no current flowing through here, all the current flowing through this 4 ohm is flowing through this 6 ohm too. Hey, take a look. We could even draw it like this, right? Isn't that true? And now there's only these 2 wires that are coming out of my node. So therefore that proves that it's in series, right? Yep, these are in series. Why can't we do this? Why is that a mistake? Why will that screw you up?
Is it because you're getting rid of the 6 ohm resistor, which is in parallel with the
That's it exactly. Remember, our whole goal is to find, our whole goal with this is to find what is this voltage. Well, if we simplify that mess, we've destroyed that voltage and we can't solve for that voltage. That's why it's so important to write down what that voltage is. And if you don't write it down, if you say, well, there's no current, so I don't need to write it down, the next thing you do is you'll transform it away. And now you'll end up finding some random voltage at some random part of the circuit, and you'll be wrong. So it's really important to keep that voltage in there so you know you can't transform away what you want to find. So your only option, since none of these resistors are in series or parallel, at least that won't destroy the thing you're trying to find, you got to do that source transform. So now you can do it. And that next step, you could do it other ways too, right? You could do a mesh. How many meshes would you have? Unknown meshes?
2.
2, you'd end up with a 2x2 set of equations. You could do a nodal. If we wanted to do nodal, we'd put our ground down here probably. How many unknown nodes do you have?
2.
2. You'd have an unknown node here, unknown node here. Again, you've got a 2x2 set of equations. That's more than you want to do. So that's a bad solution also.
Sir, I'm just curious. So in relation to the parallel voltage to VC naught, why? I understand that it's parallel and you could use that. Like, let's say, for instance, if you want, you could just say like VC naught is equal to 6 times whatever the current is once you find it. But I'm just curious though, why not? Why is that absolutely necessary? Couldn't you just simplify to a point where it's almost like the equivalent of a Thevenin or something close to it? Like you just say 6 plus 4, and then from there you could just say 6 plus 4. Then
Okay, so what happens if you try? Let's do that fast, Kyle. Let's say you do that 6 plus 4. So we've got 6 plus 4, which is 10 ohms, and then we've got our 8 ohms here, and then we've got our 9 amps here. This is what you're saying, right?
Yes, and then you could transform the.
And then the 8 and 10 are in parallel. So I don't know what that is off the top of my head, but we'll just write it as 8 in parallel with 10. Right? And then you can find the voltage, right?
Mm-hmm.
That voltage is just going to be 9 amps times 8 in parallel with 10. And that's the voltage across the capacitor, right?
Yes, that should be.
Where's the capacitor in this?
Well, wouldn't it still be
It's
on
not
the right
there.
side of it?
Nope,
Wait,
not there. It's the voltage across the 6 ohm. Where's the 6 ohm here? It's not there. You destroyed it. The moment you went from here to here, you destroyed your 6 ohm and you destroyed the voltage across the capacitor. That's why it's so important to write down where VC naught is, because otherwise you'll want to destroy it. And then you'll end up finding the voltage across some random place. Where is this voltage? This is the voltage across that current source, which is the same as the voltage across this 8 ohm resistor, which is completely unrelated to the voltage across that 6 ohm resistor.
So whenever there's an element in parallel with the VC naught, just always keep it there. Never try to change it.
The rule is if you're trying to find the voltage across an element, don't destroy that element because you'll destroy that voltage. That's the rule.
Okay.
And you're trying to find the voltage across here, which is the voltage across that 6 ohm. So whatever you do, you can't destroy that 6 ohm resistor, because if you do, you've destroyed the thing you're trying to find.
Okay.
Really easy to do, which is again why you need to write down what that voltage is across that open, even though it's an open and even though it's not affecting your circuit. Otherwise, it's not affecting your circuit, but it sure as heck affects the way that you solve it. So now let's get back to our VC naught. So here's what we want to find. We've got our 6, which we cannot transform away, because if we do, we've destroyed our VC naught. And well, I don't know what happened here. And we can source transform this. So that would be our 8 is now in series, and our voltage source now looks like 9 times 8, which is 72. Notice the pluses.
4, sir.
And where'd my 4 go? Yeah, thank you.
Sir, the 4 would be in series with the 8, yeah.
And now the 4 is in series with the 8. So now we can redraw that. Wait, if I redraw that, do I lose my voltage across my capacitor?
No, because you still had the 6 ohms.
Exactly. I haven't touched that 6 ohms. So therefore the voltage across here is still the same as the voltage across here. And I have not altered anything there. So we've got this. So important to know what you're trying to solve for, right? Because if you just collapse random things, you'll almost certainly destroy the thing you're trying to solve for. All right, now, can I add these two resistors because they're in series?
No, voltage divider.
No.
No, because we're still going to
Divider.
destroy that VC naught. So do you want to do another source transform?
Can't you just do a voltage divider?
Bingo. So you could, if you wanted to, continue to source transform. And that would put these two things in parallel, which could simplify. You could, if you wanted to, do a mesh. Now there's just one mesh. You could, if you wanted to do a nodal. You just got one nodal. But instead of doing any of those things, I'd recognize this is just a simple voltage divider. And just by inspection, VC naught is going to be the source times what? What's in the numerator?
R2.
Yeah, the one you want to find, which is 6 over 6 plus 12. If it was a current divider, what would go on top? If it looked something like 72 amps, and there was one resistor here and one resistor here, and it was 12 over here, and it was 6, how much, what's the formula for this current? It's 72 times something over this, the product, something over the sum, just like this. What goes on top here?
12 times 6.
36? No. So here, this is a voltage divider. You put the one that you want to find it across the 6, so that goes in the numerator. This is a current divider. What goes in the top?
Would it be the product?
12 times 6.
It will be.
You know, it's not the product, because
12.
think about it. If it's the product, then the units on the product would be ohms squared. The units on this are ohms. You'd end up getting the current is equal to amps times ohms. That's the voltage. That doesn't make sense. So it's got to be ohms on top to cancel the ohms on the bottom. When multiplied by the current gives you current. So what's in the top?
It's 12 times 6.
We just said it's not the product. We just said it's not 12 times 6, because that would give you ohms squared up here, divided by ohms gives you ohms times amps, which makes the entire thing volts. And it doesn't make sense to say the current through this is some amount of voltage.
Shouldn't it still be 6 then? On top?
Okay, you guys really need to go back and study what voltage dividers are and study what current dividers are before you take this test, because you'll be missing easy points. It's the other one for current, and it's the same one for voltage. Now we can simplify this. This would be 72 times, let's see, I'll divide top and bottom by 6. So that gives me 1 over 3. So that's a third of 72. So that gives me 24 volts. And that's my VC naught. But wait, we need to find I of T, right? So do we need to find I of naught? What do you think, Jack?
I mean, don't we always have to find both? Like, isn't that like a given?
Yeah, don't we always need to find voltages and currents to start off with?
It's either the voltage of the capacitor or the current in an inductor, right?
Yeah, you really, really want to go back to and follow.
Can we just use Ohm's law to convert the voltage?
You don't need to. You don't want to. The very first step is to draw it for time less than 0 to find either VC naught or I sub L naught. No matter what you're asked to find, exclamation mark, find just the voltage across the capacitor or the current through the inductor. And if you find anything else, you're wrong. That's because in step 4, you're going to substitute it into this equation. If there's a capacitor, you're going to use this. If you find any other initial condition other than VC naught, it doesn't belong there, and you just wasted time. And you don't have enough time in this test to be randomly finding stuff that doesn't help. If you're at the point that you haven't really internalized this, you haven't done enough problems yet. You've got to just keep going with these things until you know what this is. Until you know my first step is going to be draw it for time less than 0 to find this or this. If you know you're going to draw it for time less than 0 and you're not sure what you're going to find, the likelihood that you're going to find the thing you're supposed to find is pretty close to 0. There's a lot of other things that you could potentially find here. Let me just make it perfectly clear. Your first step here is done. If there's a capacitor in the circuit, draw it for time less than 0, and the only thing you find is VC naught, and then you're done with step 1. If there's an inductor in the circuit, the only thing you find is the current through that inductor, and then you're done. And the reason why you find that is that if you know that this is the voltage across the capacitor for time less than 0, then that's got to be the same as the voltage across the capacitor for time equals 0, even after the switch is flipped.
Because at equals 0, there's no current flowing through the circuit.
No, there can be lots of current flowing through the circuit at time equals 0.
Or,
There will be for
sorry,
this.
there's no voltage.
Capacitor,
Wait, there's no voltage flowing through the circuit? Voltage doesn't flow. Only current
capacitor
flows.
wouldn't
It
accept,
doesn't make sense to talk about voltage flowing. Voltage is a pressure.
No, like there's no voltage going across the capacitor at equals 0. It
So
hasn't.
So you've got this capacitor, and for time less than 0, it's charged up to a 20 volt pressure. And it's like that for all time less than 0. Are you saying that at time equals 0, it all of a sudden and instantaneously snaps back here, moving all of the charge that was stored in here instantly within a fraction of a second, moving it this way and normalizing it with that much charge moved this way? In a fraction of a second, you get finite charge removal, so you've got an infinite current?
no, sir. The capacitor can't take abrupt changes in the voltage.
Right. The rule for capacitors is that the voltage across the capacitor is continuous. If you know what it is for all time less than 0, it's got to be the same as time equals 0. Physically, what's going on is that this thing can't instantaneously change position. If you could instantaneously change this guy's position, you'd be instantaneously moving charge. You'd have an infinite amount of current. You can't do that. Similarly, the current current through the inductor is continuous. You can't instantly change the current through an inductor. If it does, it would develop an infinite amount of voltage across it to resist that magnetic field collapsing. So if you know what VC naught is for time less than 0, you know what the voltage across that capacitor is for time equals 0, even 0 plus. It's got to be the same as 24 volts. Hasn't changed. But I want to emphasize, though, that the goal of first step is to draw it for time less than 0 and to find VC naught, and that's it. Thumbs up. Okay.